Hello everyone, I'm Haokun Chen Winton. Today we are going to discuss a basic concept in linear algebra, which is the rank of a matrix. Rank of a matrix can have many applications in mathematics and statistics, but before we go on, please make sure you understand what matrices and vectors are, as well as the basic operations. If not, I suggest you to watch videos about these topics, and you are welcome to come back once you have the foundation. The rank of a matrix has several definitions, but instead we go straight to them. Let's consider the following problem. Suppose we have three vectors, A, B, and C, in a three-dimensional space. The question is, can we reach every single point in the XYZ space by just only using these three vectors in some linear operations? The answer is yes. Let's say the point 2, 0, and 1. We can reach there by subtracting B from C, then adding twice of A. Here we introduce a concept called span, also known as the vector space. Generally, a span or a vector space of n vectors contains all possible points reachable by these n vectors. Notice that the maximum dimension of the image span is 3. In other words, the vector space is three-dimensional. Now let's consider the case of P, Q, and R. It looks like we have three vectors, but in fact we have only two. Actually, R is the sum of P and Q. It is just some simple linear combination of P and Q. So down to the earth, we have only two vectors to create a subspace in R3, which is also called a vector space. We cannot reach every point in the XYZ space, therefore the maximum dimension of the space is 2. When we align the three vectors to form a 3 by 3 matrix X, for instance by row, the maximum dimension the row vectors can span is equivalent to what we call the row rank of X. So if X is equal to this matrix, the row rank of X is equal to 3. Column rank is a similar thing, except it represents the maximum dimension the column vectors can span. We can see that 1, 1, 1, 0, 1, 1, and 0, 0, 1 also span a 3D space, because none of them can be expressed by the other vectors. Therefore, the column rank of X is equal to 3. Here we can see that the row rank of X and the column rank of X are the same. The truth is, the row rank and the column rank of any m by n matrix, and it is not necessarily square, is always the same. We call it the rank of the matrix, and we denote the value as rank of X. The proof is not introduced here, as the difficulty is beyond our level. For easier learning and motivation, what we have discussed by now is the geometric interpretation of the rank of a matrix. Now we will introduce a more formal definition. The rank of a matrix A is the size of the largest collection of linearly independent columns or rows of A. This may simply be interpreted as the rank of a matrix A is the number of linearly independent columns or rows in A. Perhaps I can explain a little bit on linear independence. For n vectors to be linearly independent, any one of these must be impossible to be expressed in terms of the other n minus 1 vectors by linear operations. For example, these three vectors are linearly independent because they don't have any linear relationships. You can pause the video and have a check. On the other hand, these three vectors are linearly dependent because the third one is the sum of the first one and twice of the second one. Bear in mind that column rank of X equals row rank of X equals to the rank of X. This is identical to the statement rank of X equals to the rank of the transpose of X. No matter an m by n matrix X is square or not, the rank of X is at most the minimum of m and n. We can understand this by imagining a 2 by 3 matrix We have 2 row vectors and 3 column vectors. Since we can only span 2-dimensionally with only 2 row vectors, the row rank is at most 2. By the equivalence of row rank and column rank, the column rank and the rank of the matrix is at most 2 also. If rank of X is strictly less than the minimum of M and N, the matrix is rank deficient, otherwise it is in full rank. Next, we will talk about some properties of the rank of a matrix. Let A be an M by N matrix, B be an N by K matrix, and C be an L by M matrix. Consider the matrix AB. It has the dimension of M by K, so the rank of AB is at most the minimum of M and K. Since it is obvious that M is less than or equal to the minimum of N and N, and on the other hand, K is less than or equal to the minimum of N and K, we can conclude our first property that rank AB is less than or equal to the minimum of rank A and rank B. Then, if rank of B is N, the above would become rank AB less than or equal to the minimum of M and N, which is equivalent to minimum of M and the rank of A, which is our second property. Similarly, the dimension of the matrix CA is L by N. If the rank of C is M, following the similar argument, we have rank of CA is less than or equal to the minimum of M and the minimum of M and N, and it is the rank of A. Also, here is the third property without proof. The rank of the product of A and the transpose of A, no matter what the order of multiplication is equal to the rank of A and the transpose of A itself. It is tedious to check graphically to see how many dimensions the vectors could span, especially for higher dimensions. Luckily, there are 2 ways to calculate the rank of X, one of which is by row echelon form. A matrix is said to be in row echelon form if all 0 rows are at the bottom of the matrix, and the leading coefficient of a non-zero row is always to the right of the leading coefficient of the row above it. This is an example of a matrix in row echelon form. Now rank of X can be found by transforming X to its row echelon form and count for the number of non-zero rows. Here are some examples. Let X to be this matrix. We first subtract row 3 from row 1 to replace row 3. Then subtract row 3 from row 2 to replace row 3 again. We now obtain the row echelon form of X. Then, the rank of X is the number of non-zero rows, which is 2. Now let's consider Y. We first perform similar transformation to obtain this matrix. Notice that row 3 and row 4 is now the same. We finally replace row 4 with the difference between row 3 and row 4. Lastly, we add row 3 to 17 times of row 2 to replace row 3. Y is now transformed to its row echelon form, and its rank is 3. The second way is by determinants. A non-zero determinant implies that the matrix is in full rank. Otherwise, select any square submatrix with 1 degree less and compute the determinant. If the determinant is non-zero this time, the rank will be full rank minus 1. Repeat the process until the rank is determinable. For example, suppose we have this matrix A. The determinant of A is calculated as shown here. We see that it is non-zero. Therefore, the rank of A is 3. We will now discuss one of the applications of rank of a matrix in mathematics. Rank of a matrix has a lot to do with systems of linear equations. Let's see how they are related. A set of linear equations is said to be consistent if there is at least one set of solutions. Otherwise, it is called inconsistent. There are several ways to determine the consistency of a system of linear equations. We can perform Gaussian elimination and inspect the last row of the augmented matrix, or evaluate the determinant of the coefficient matrix. The third way is by the rank of matrix. Let's have a look. Suppose we have an n by n system of linear equation Ax equals to b, where A is the coefficient matrix, x is the variable vector, and AB is the augmented matrix. If the rank of A, B, and the number of rows are equal, the two matrices are in full rank. This means all rows in the system are independent, so we have unique solutions. If the rank of A equals to the rank of AB but less than m, the two matrices are rank deficient. This means there are dependent rows in the system, such as this example, where row 2 is the twice of row 1. We will have infinitely many solutions. If the rank of A is smaller than the rank of AB, it means there are contradictions, like this example, when we divide row 2 by 2, we get 2x plus y equals to 10.5, contradicting the first row. We will have no solution then. Another application of the rank of a matrix in statistics is the multivariate normal distribution. A vector of random variables x with length n is said to follow multivariate normal distribution if any linear combination of x1 to xn follows univariate normal distribution, and there exists a vector z with length k whose components are standard normal random variables, a vector mu with length n, and an n by k constant matrix A such that x is equal to Az plus mu, where k is the rank of the covariance matrix sigma equals to the product of A and transpose of A. Multivariate normal distribution is an advanced topic in statistics. The purpose of this slide is to illustrate the importance of rank of a matrix in statistics, so it is okay if you didn't understand anything of what I've just said.
After a brief understanding of the rank of a matrix, let's do some exercise to consolidate what we have learned. Let P equals to this matrix. If the rank of P is 2, what is the value of X? The answer will come straight away, so if you want to figure it out yourself, pause the video now. The order of P is 3, but the rank is 2. That is, P is rank deficient, so the determinant is 0. We can compute the determinant as shown and see that x is equal to 2. Let xij, I from 1 to m, j from 1 to n, be the jth observation of the ith sample following a PDF of fi xi. This matrix is in full rank. What is the joint PDF of x1 to xm? Since the matrix is in full rank, all rows are independent, which implies that all n samples are independent. We can then find the joint density function by taking the product of the individual PDFs. Question 3. Let B be this matrix. If the rank of B is 2, find the values of K. Then determine whether this system of linear equations has unique solutions. The same as before, rank deficient implies a zero determinant. We can find the values of K by solving a quadratic equation. Then you should notice that the coefficient matrix of this system is actually the transpose of B. We know that the rank of the transpose of a matrix is the same as that of the matrix itself. So the coefficient matrix has the rank 2. Since it is rank deficient, the system do not have unique solutions.
So that's all for this video. I hope you have a good foundation on the concept of rank of a matrix. There are still many other applications in mathematics and statistics, but we keep that for your future exploration. So have a nice day. Thanks for watching.